Good morning. Here we go. I think we have a worksheet today. We do? Okay. Thank you. I always forget to check in the morning. I'm so busy. This is one of today we have the perpendicular and angle bisector theorem. So you can see we have this perpendicular bisector theorem we're going to talk about, and we have this angle bisector theorem we're going to talk about as well. I don't like these theorems, so I'm not going to talk about them too much because I would rather go back to triangles, okay? Because it's actually much easier if we just think about the triangles, okay? So let's look here. So we want to be able to use and apply the bisector theorems, but really, I just have one question for you. Are the triangles congruent? And so when I look at this picture, how many triangles? Two. Well, technically three, but yes, two. We have a left side and a right side, right? Okay. And the big one. Yeah, oh, yeah, okay. So, there is a left triangle and a right triangle here. And, okay, so when we're looking at these two triangles, the left triangle and the right triangle, one question. When you look at the markings on there, are the triangles congruent? No. Alexis, why? HL. Yeah, that it is, well, no, actually, it's not HL, but you're on the right track. What else do we know given this picture? I have no idea. Okay, we have two right angles. Those are congruent. Reflexive, ladies and gentlemen. We do have a reflexive side there. And so when we look at these two triangles, we have a pair of sides congruent, some congruent angles. We have two right angles. Those are absolutely congruent. And then we have another side congruent. So are the triangles congruent? Yes. Yes, by side angle side. Okay. These triangles are congruent. And what it means is that we have two congruent triangles, so there are 6 things that I know that are congruent in these triangles because they're congruent. There are tons of things that I know are congruent. So if these triangles are congruent, I can write a congruency statement that says, hey, let's see, triangle ADC is congruent to triangle what? BDC, very good. BDC. And because you guys just took this test and did very well on this question, when we have a congruency statement, I know that angle A is congruent to angle B. Angle A is congruent to angle B. I know that angle D obviously is congruent to that angle D in there. And angle C, that little guy up here, is congruent to this little guy, of course, okay? But I also know, hey, over here, segment CA, this side, is congruent to BC, this side over here, okay? So just because we have congruent triangles, we know a ton of information, okay? Does that make sense to you? Okay. And that's what this perpendicular bisector theorem says. It says that if I have right angles, if we have perpendicular lines, that gives us right angles, right? And I have a pair of legs that are congruent, that's the AD and the BD side, then this side AC, segment AC, is congruent to segment CB. We already knew that. It had nothing really to do with being perpendicular. Does it help? Sure. But we can just say, hey, I know those triangles are congruent. And so I know a whole lot of information, okay? Now, the converse of the perpendicular bisector theorem, if a point is equidistant from the endpoints of a segment. So what are they talking about there? This is the hard part of these things, is really just deciphering what they're talking about. What did you say was? So if a point is equidistant from the endpoints of a segment, well, here's my segment AB, and the point that they're referring to is point C. So what do they mean by that?
Halfway between.
So eventually, but what they're saying, to be equidistant, then equidistant means that the length from C to the endpoint is the same on the other side, from C to the endpoint. So equidistant is referring to these two segments being the same distance apart, being the same distance away from that point C. So if those two legs happen to be congruent, then C happens to live on a perpendicular bisector of the segment. So if you have congruent legs, then that point C happens to be on a perpendicular bisector. So first it's perpendicular, but that segment CD also bisects segment AB. So it cuts it into two equal pieces. And so we know if our two little legs of this, it's an isosceles triangle essentially, then a line exists through C such that CD is perpendicular to AB and AD is congruent to DB. So we get perpendicular lines and we get two congruent segments. So that's really the one that's kind of interesting. All right, so let's look at a few of these questions here. Number one, we want to find the value of x. So once again, I want to look at the markings on this page. I don't need to know a ton except my congruent triangles. I see, how many triangles here?
3.
3, okay. 3, a left and a right and the big one, right? Okay. But really, I'm focused on the left and the right triangle. Are the left and the right triangles congruent?
Yes.
Yes. Why?
Because they're both right angles.
Side angle side, because reflexive side. So the triangles are congruent by side angle side. We have two pair of sides, pair of angles, and then another pair of sides congruent, all right? So those triangles are congruent, which means if we know that they're congruent, then I also know that these two sides also happen to be congruent. So what can I write? What equation can I write here?
7x plus 24 equals 13x.
Good. 7x plus 24 equals 13x minus 48. Okay, because they're congruent. So I'm going to go ahead and subtract 7x. That gives me 5x. Right? No, it doesn't. It gives me 6x.
Wow, you're not on the game today. None of us are.
It's Friday, you guys.
It's been a long week.
All right, and then we need to
I need to hit the hot tubs.
add 48. So add 48, 72 equals 6x. And then was 12. Divide by 6, we get x equals 12. Okay, and it did ask us to find the value of x there, so we're good to go. All right, let's look at number 2.
I say reflexive.
So are these triangles congruent? I heard reflexive. We do have a reflexive side.
No.
But are these triangles congruent?
I don't think so, because one line is higher than HL.
HL, very good. Yes, we have right angles, and this This pair of congruent sides are the hypotenuses, and we have a leg here. This is congruent by HL. Very, very good. Now, if we're congruent by hypotenuse leg, then we also know what else is congruent here. Yeah, these bottom legs are also going to be congruent by CP, Congruent parts of congruent triangles are congruent. CP, All right, which means I can write what equation? 17x minus 3 equals 9x plus 13. And we could go from there. You would get x equals 2. Do I need to do that or no? Yeah, okay, I don't think so. All right. Number 5? Okay, number 5. Well, again, we can just burn through these pretty quickly again, because I think, so what do we know? We have a left and a right triangle. Are they congruent? HL again. We have a reflexive side, and so the hypotenuse and the legs are congruent, so we're congruent by HL. So I have two congruent triangles, which means, what else do I know? Yeah, so Waz, I'd really appreciate, Waz, I would really appreciate you stop talking. Do you understand?
Yeah.
We have the third set of sides must be congruent by CP. And so, yes, you are right. Then we can say that 5x minus 11 is equal to 3x plus 17. And we could solve that from there.
2x equals 28.
X equals 14. Are we done?
No.
No, we got to find AB. So we got to find the length of AB, which means, what do we have to do? Plug it into both of them. So we'd have to do, so 5 times 14 minus 11, which is 59. Oh, what's this one going to be also? 59, because we know that they're the same, right? So 59 plus 59 equals 118. So 118 inches or whatever. Okay, so questions on this one? It's pretty easy, right? We just have to think about congruent triangles. Like, did we need to know this?
Not really.
Not really, right? If we know our congruent triangles, ladies and gentlemen, everything builds on that from here on out, okay? It's a great way to think. So let's turn the page.
I'm scared.
Okay, number 7, where they're giving me ordered pairs, what formula do you suppose we're going to have to use? Distance formula, ladies and gentlemen. The distance formula is the square root of?
y2, y1, it's x2 minus.
Yeah, so usually start, so x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Though technically, you're not wrong, Quentin. They can be in any order because we're just adding them. Okay. So there we have the distance formula. Now, I like to draw a picture. Again, when in doubt, graph it out. Draw a sketch. So this says, if JK is formed by point J at -7, -8, and K at 1, 4. So I'm just going to pretend. I'm just going to plot them and sort of pretend. I'm not plotting them for real, okay? But here's J and here's K. J is at -7, -8, and K is at 1, 4. And I know that's not where they would be placed, but it doesn't matter. So this is segment JK. So there's a segment connecting them. We want to determine if L, which maybe is, I don't know, we're going to pretend, again, it doesn't matter here. I'm just going to put it here. If L at -9, 2 lies on the perpendicular bisector. So of segment JK, the perpendicular bisector of segment JK. So is there a line that goes through L and is perpendicular and bisects that segment JK? So we're trying to figure that out. Well, this is where that perpendicular bisector theorem came into play. Because if it's on that perpendicular bisector, then this segment should be congruent to this segment. So this is what I need to know. Are these two segments from L to the endpoints, are they the same length? Okay, that's what that second theorem was. So I need to figure out the length of JL using my distance formula. So between J and L, and again, I wrote my ordered pairs so I could do this easily. So x2 minus x1, so negative 9 minus the negative 7, quantity squared, plus 2 minus the negative 8, quantity squared. Let's see, that becomes negative 9 plus 7, which is negative 2, and we're going to square that, which becomes 4. And then here, this is 2 minus a negative 8, which is really 2 plus 8. So that's really 10 squared, which is 100. So this is the square root of 104. And I want to compare that to this other segment, LK. We want to know, are they equidistant? And if they're equidistant, if they're the same length, then we're on a perpendicular bisector. So again, using L and K, I have negative 9 minus 1, quantity squared, plus 2 minus 4, quantity squared. Negative 9 minus 1 is negative 10, which squared is 100. It's always going to be positive. We're squaring the whole thing. And then 2 minus 4 is negative 2. Squared is always. And so again, we get 104, square root of 104. So yes, it is on the perpendicular bisector. Okay. And what's interesting is wherever, like you can imagine, if L wasn't here, if we're on a perpendicular bisector, maybe L is down here, then these are the same length. And it's sort of a, you know, I see this as like wires. Do you see the wire? Kind of. Like, so this is like a little, I don't know, maybe an antenna, okay, standing straight up. And then these are what are called guy wires. And they would be the same length if they're the same distance away from the base of the pole. So kind of interesting, but that's how I sort of visualize this, okay? That wherever, however tall that point is on your antenna, if we're the same distance away from the base of the post, then these guy wires would be the same length. Does that make sense to you? Can you imagine that? Yeah, so you imagine, like, this is like, so imagine this line is like an antenna, all right, straight up, perpendicular to the ground, okay? And so if I count 10 feet to the left of the pole and 10 feet to the right of the pole, and I attach wires from my antenna to the ground, will those wires be a different length, or should the wires be the same length? They should be the same length, right?
I think the only time I've ever seen those is a few times with elementary school.
Yeah, and so, you know, it's kind of, you know, that's how I sort of think about this. Here we have a perpendicular bisector. Wires from the same point should be the same length on the other side. Does that make sense to you? Can you sort of visualize that? Okay. So, once again, we have the angle bisector theorem. And again, I'm not a huge fan of these theorems because if we think about a couple of things a little more carefully, we don't have to learn a new theorem, okay? So first of all, for the angle bisector theorems, we have this this word equidistant, and we haven't spoken about this word being distant from something. The idea that I have a wall. Let's say I have a wall, okay? And I want to know how far is point P away from the wall? How do we measure the distance from a point to a line? Oops. So my question is, if I measured this way and said, hey, it's a distance of 10 centimeters, is that how you would measure your point to the wall?
No.
That doesn't make sense, does it? Okay. And so do I go this way and say, oh, it's straight to it, so that's a distance of 12. Is that the distance from the point to the wall? No, it's not. And so how do we define the distance between a point and a wall? How far am I away from the wall? Look at it, there it is over there. Is it that far away? No. How do I measure this?
Straight back.
Straight back. I need a better word than straight back, because straight is a line. Like, I can go straight to that wall, too.
Steps back.
So, 3 steps away. Versus if I walked this way, I'm 5 steps away. How do we get to the wall?
You bisect the wall.
You walk through it.
A ruler.
No, not that.
But, I mean, one was 5 steps away, one was 3 steps away. Which is the better answer? 3, why? It's the shortest. It's the shortest distance to the wall. Well, it turns out that the shortest distance to a wall is the right answer. The shortest distance to the wall, maybe this is a 6, I don't know, okay, let's say that's the 6, all right? It turns out that the shortest distance is always perpendicular to the wall, okay? So when we are measuring a distance from a point to a line segment, from a point to a wall, we want to be perpendicular to that wall. That will always give me the shortest distance, okay? Because if that's the shortest distance, if I go slightly, there's the hypotenuse, that's longer, isn't it? Okay? And here I do another one. This hypotenuse, because again there's a right angle there, is longer, okay? Does that make sense to you? So the shortest distance always occurs at a right angle when we're perpendicular to that wall. Okay, so now I want to read this angle bisector theorem. It says, if a point is on a bisector of an angle, okay? So here I have this big angle A here. AD, ray AD, is bisecting the angle. It has cut the angle into 2 congruent angles, 2 little baby angles, okay, that are congruent. And so we're talking about if a point, and that would be if point D, right here, lies on that angle bisector, then the point D is equidistant from the sides of the angle. And so what that's saying is point D is, if we measure the shortest distance perpendicular to the side of the angle, it is equidistant, meaning it is equally spaced from the side AB of the angle, and it's the same distance away from side AC of our angle. All right? It's equidistant, the same distance away. Of course, to get that distance, we had to be perpendicular to the side of the angle. Okay? It's a really complicated picture. So point D is the same distance away. It gives us a right angle and it gives us congruent legs. Okay? When we look at these two triangles, the top triangle and the bottom triangle, are these two triangles congruent? There's a lot of ways these are congruent. We have, just from this picture, we have these right angles, yeah? Yeah, okay. And we have another pair of congruent angles, yeah? Yeah, okay. And so we have angle, angle, side. We had the reflexive side, which is also angle, angle, side. All right. So they are congruent by angle, angle, side, lots of ways. All right. So again, looking for congruent triangles, I think, is the easiest thing to do here. So if ray AD bisects your angle, then we get perpendicular. If we're perpendicular to the sides, then BD is congruent to DC, is what this picture is showing us. BD is congruent to DC. That's the theorem. This picture, again, looking at this picture and what we're given, I just want to ask you, are the two triangles, the top and the bottom triangle, are they congruent?
Yeah.
What else do we know? So B and C, we know are congruent. They're both right angles. And we have this pair of congruent legs. What else do we know for sure? Reflexive side, sure. And so we have right angles. How are these two triangles congruent? Yeah, again, they're congruent by HL. And because they're congruent by HL, I know that these two little angles happen to also be congruent by CPCTC. Okay. Which means if these two little angles are congruent, then AD is also going to be called a angle bisector. And that's what the converse says, that AD, ray AD, is bisects angle BAC, big angle BAC. I don't like these theorems. Again, I think they're really wordy. I think that there's a lot going on in them. But really, hey, we've got congruent triangles. We know a ton of information. Okay? So let's look at number 8. And again, I don't care so much about the theorems. I care more about, look at our two little triangles, the top triangle and the bottom triangle. Are they congruent? What else do we know? We have a pair of right angles, and we have these two angles that are congruent as well. What else do we know? Reflexive side. So are the triangles congruent? By?
Equal side angle?
No. Angle, angle, side. Angle, angle, side. Angle, angle, side. Angle, angle, side. All right. And so if the triangles are congruent by angle, angle, side, tell me about the segments they have listed here. They're congruent. These must be congruent by CPCTC. And so we can write the equation 4x plus 30 is equal to 9x minus 5. And we can solve from there. It turns out x is going to equal 7. Look at number 11. Look at number 11. Look at our triangles. What else? We've got a pair of angles that are right angles. We got a pair of legs congruent. What else do we know? Reflexive. That was what I was going for right there. Reflexive side. Are the triangles congruent? By? No. Hypotenuse, leg. HL. Yeah, HL. Hypotenuse across from the right angle and a pair of legs. All right, which means the triangles are congruent, so I also know, hey, these little angles must be congruent by CPCTC. All right, everything is by congruent triangles. It's really quite fabulous. So what equation can we write?
8x minus 32 equals 3x plus 3.
Beautiful. All right. And again, we can solve. Go through the process. We get x equals 7. What do I have to do once I get x equals 7? Plug it in to xwz, which is right here. So 8 times 7 minus 32. The measure of angle xwz would be 24 degrees. All right. Do you have questions for me?
Nope.
All right, number 12, just real fast here. Number 12. I got 2 triangles, I see. Well, 3 technically. Oh, no, that's a quadrilateral. 2 triangles, I see. Are they congruent?
Yes.
What else do we know?
Reflective.
Reflexive. And so these triangles are congruent by HL again. Again, this is the hypotenuse, this is the leg, so this is HL. And so if the triangles are congruent, I also know that, hey, these angles must be congruent as well. In addition to these little babies up here, they're also congruent little angles. Okay. And so what equation can we write?
2x plus 20 equals 5x minus 37.
Mm-hmm. And we can solve from there. But I don't want to do it anymore.
3x equals 57, so 57 divided by 3 is 9.
It's true, x equals 19 is correct. Which, of course, is not the answer to the question. But that's okay. All right. Do you have questions for me?
No.
All right.